Hello everybody, this is part 2 of the polynomial intro lesson. You're looking at this quadratic right here. It is in factored form already. So what I'm going to do is switch over to the screen and we'll talk about this thing real quick. Alright. So a couple things to think about based on your chart that I had you fill out I think 2 weeks ago now, maybe 3 weeks, I don't even know. But the power function chart is still going to be a key thing even when we get into polynomials. Many of you, like myself when I was your age, are bulldozers and you want to just expand this. There's really no need in this particular case to expand it. However, it would do this. This is a polynomial. The leading term is x squared. Leading coefficient is 1. The idea, though, that it is 3 terms, all of which are power functions. Now, you might be like, power functions, what do you mean? Well, x squared, x to the first, and x to the 0th. All right? Constant, linear, quadratic. So the idea is, what do we do with this thing? And we already have the roots. We have the y-intercept, 0, negative 12, and we have the roots of negative 3 and positive 4. So now, the idea of what do you do with the chart? Why do I need this? Well, what we're talking about for power functions still apply. We want roots, aka x-intercepts. We want y-intercepts, asymptotes, and in this case there are none. All right, which is good. But the idea is we're just going to figure out, well, what do we do? Well, we know this thing, this x squared term, that is the dominant term, that is the lead term. So from your power functions chart, x to square, x to the second, x to the fourth, x to the sixth, x to the eighth, all basically had that shape. So we know that this too will have that shape. And that's kind of what we're talking about here. That is a polynomial function. Again, we don't really need to expand it. We can get all our info right here. To find a y-intercept, it's as always, you just fill in x is equal to 0. If you fill in x is equal to 0, you get back real quick that you have your y-intercept. This is in factored form. So the roots are great, and they're easily obtainable because they're the two values just like normal that you're used to. And then we're going to get into a little bit different approach, and where does the limits come into play? Well, if I approach negative 3 from the left, I'm getting a number that is super close to 0, but positive. So the limit will definitely equal 0. But if we go slightly before negative 3, the answers will be really small, but positive. If I go from the right-hand side of negative 3, so I'm approaching from right to left, then the limit will still equal 0 for sure, but these values will be negative. And also, to think about this in a couple of different ways, the graph of x plus 3 is a line, all right? And this function, if you blow it up just around the root, it would resemble the appearance of a linear function, even though ultimately it is a quadratic, okay? So we're talking about sign change plus to minus, okay? If we do the exact same stuff, but we approach 4 from either side, 4 from the left, 4 from the right, we will get 0. But if we're slightly below 4, like 3.99999999999, the answer will be negative. If we're slightly above 4, 4.000001, we will get positive. So there is sign change there. Again, the graph looks like a line. There has to be sign change. And overall, the same for the negative 3 as well. If I take away approaching it from the left to the right, the limit still is 0. Okay, because remember, limits are literally just what is the y value approaching as the x value approaches, in this case, negative 3 or positive 4. Okay, that's number 2. All right, let's see. Hopefully this won't freeze out on me again. I hope it won't. It's not looking like it is, which is good. All right, now we got this guy right here. We're going to talk about that one. I'm just going to have to quickly erase just so I have some action. And this is an h of x function. So the h of x function is 3 linear terms, the product of 3 linear terms. And what we're doing there is we're basically saying, okay, overall, if I expanded this all out, which I'm not going to, if I distributed this, it wouldn't be that bad, just a little tedious. This is going to look like a cubic. So what does a cubic look like long term? It looks like that. Okay? So we expect to get a graph that looks like that. And now the idea also, x times x times x is positive x cubed. So this thing will look like that. If we did get a negative number out here, remember, it's the reflections, our transformations that we've learned since day one. All right, well, since October at least. So here's our scenario. My roots, -5, -3, and +4. So I have these roots. I would like to find the y-intercept. To find the y-intercept, I'm just going to plug 0 in for x. And what am I going to get? I'm going to get 5 times 3 times -4, which would mean that my y-intercept is -20 times 3 is -60. So I got to expand this down here. There we go. That's good enough. Close enough for government work. So now I have got to hit these 3 points and this 4th point for the y-intercept. And so what was the purpose of talking about overall, what is it going to behave like? Well, this polynomial graph will behave like its leading term long term. So the idea there is what we started off in part 1. As x goes to infinity, h of x basically behaves like x cubed. And as x cubed goes to infinity, all right, or sorry, as x goes to infinity, so will the graph of x cubed. So I know that I have that scenario happening. And I'm going to go back to the big screen. I didn't realize that. I wasn't on there. So the big screen shows us this. Okay? These limits right here. All right? That's going to go to infinity. So basically I have the same behavior as a cubic, but what's going on short term now? So there's our long term idea. It's got to look like this, like a little snake graph, or like your math dancing that we were saying before marathon. And now the idea is x plus 5 is a linear function. It's got to look like a line. When we go through -5, there's got to be sign change. So we're going from negative to positive. We've got to hit -3, so it's got to turn around and hit -3. And also it has to change signs, because we have to hit this point down here and then reconnect here. So this graph, without doing it really any work besides finding the x-intercepts and the y-intercept, is going to look like a cubic long term. Like if you expanded it all out, and if you put it in Desmos and you just kept on expanding out, get your x's bigger and bigger, then it would basically take on this shape right here. Short term, however, it has to hit -5 because it's a root. It has to also hit -3, but it has to also hit 0, -60. Now, what if we try to draw this differently? What if I can hit -5, but then I have to hit -3, but I don't want to cross the x-axis? It would have to look like this. And then, wait a second, I couldn't cross the x-axis again. I'd have to come down here, and then I'd have to come down here. So it would still have the same shape, but watch this. This would mean I would have, based on your stuff from Khan Academy as well, to reiterate their points, I would have no sign change here, which means I would have to have a double root. So I would have to have that going on up there with a 2. And at -3, I would also have to have a 2 right there. Maybe even more, maybe a 4. Okay? So, and then that would change the y-intercept, of course. But there's no way to draw that correctly, because now we're talking about a squared times a squared is a 4th times an x is a 5th degree, which is not the graph that's given. So that green graph doesn't make any sense whatsoever. The black graph, the only way you can actually draw that thing. All right? That's kind of what we're after right now. Doing a little exploratory. It will make hopefully a little more sense when you actually see the worksheet, which is super easy. Now, this is a bummer. We have that nice new fancy room. I was going to have you guys come off by 8s, get into groups when we did this, and then have you guys put the stuff all over the whiteboards, and then you can kind of do a gallery walk around the classroom. It's actually worked out really nice last year, and I was going to do it with you guys this year as well. There's that idea of that double root. What does that look like? Okay? So we're going to keep on keeping on. Here's the notes that we're talking about right here. The general formula for any polynomial function is written as this. look super intimidating? Not really. It's the same standard form that you guys have been writing for years in math. The gist is this. I have x to the biggest power. The a sub n is just the coefficient that goes along with the x to the n term. That's why the n's match. The n minus 1's match because I'm talking about the coefficient that goes with the next degree lower, the next exponent lower. So on and so forth all the way until you get a constant. Okay? Here's these things defined for you. I have a star next to the leading term because that is what's going to dictate the overall shape of the graph. Now, what I mean by that, in case we lost some of you or I'm going a little too fast, I don't really know, but I'm trying to be pretty good about anticipating some questions if we were in class. All right, so the gist is this. If my leading term is the following, something to the x cubed, then I know my graph is going to look like this on some level long term. As x goes to the infinities. Okay, that's how the graph's going to look. If my graph was x to the 7th, it's going to have the same shape pretty much as x goes to infinity and as x goes to negative infinity. So the key thing here to look at is these are all odd and they all have the same overall shape when we let x get really big. All right, if your leading term was, let's say, an even function, and I shouldn't say that, an even powered function, let's say your leading term was x to the 4th, then your overall shape would be a parabola. If it was x squared, this is stuff that's in your wheelhouse, it would be a parabola. If it was x to the 18th, it would still be, long term, a parabolic shape. Now, what we're going to get into is what's going on short term. So how do the roots play in and how do the y-intercepts play in? Well, basically, if we're going, so these are all long terms. If we're going to go short term on this bad boy, you might have a graph that does this. All right? Overall, same general shape, same U shape, but maybe it has some turns in it. X squared is going to look like x squared, so I'm going to skip that one. X to the 18th, however, that could get wild. We could have something that looks like this. But overall, same idea. If I zoomed out, I would get basic U shape. These humps would even out and kind of look like this giant parabola if I let the scale get big enough. All right, so that's kind of what we're talking about right here. That's the main thing that you guys had on that power functions chart. You should have that chart out at all times when doing anything in this entire unit. So power functions builds into polynomials. Why? Because polynomials are literally just the sum or difference of power functions. Okay? And we're frozen. Wait a minute. Come on, baby.